Hi, it's me again. As you can tell, this is a very different talk because the line is in blue instead of green like last time. Yeah, I'll just get started. So this talk is going to be talking about some work we've been doing on basically a different way to define your MLIR operations in a more declarative way. You can sort of view it as an extension to the sort of constraints that Ivan introduced in his IRDL talk. And this is the system that we've rolled out in XDSL, which, in case you don't know, is sort of a Python clone of MLIR. And yeah, we're using this sort of throughout the system, and I'm going to sort of explain how it works, where we're at with the system, and what we're sort of planning on doing next with it. So before that, I'm going to take a small step back and sort of ask, what does an operation definition actually do? So in MLIR, you've defined some operation, but what does that actually mean? Have you just given it some name? Well, not really. So firstly, the operation will usually have some associated verification with it so that it can check that its inputs are the right type and check that it has the right number of inputs and outputs, and it might have various attributes that it expects to always possess. All of this is built into this operation definition. There's this second sort of category, which I've called inference here, but basically this corresponds to sometimes we want to specify an operation with incomplete data and be able to build the rest of the data, be able to infer what the rest of the data is from that incomplete data we've been given. So the two main examples I have of this are builders. You might want some very small interface for building your operation, but it needs to still fill in all this stuff. And then maybe the more familiar one is parsing, where our custom formats don't have to have loads of extra unnecessary data. The last thing I'm not going to talk about so much is accessors, but this is another thing that came to mind of what your operation definition can do for you. So I'm going to go with the simplest example I could think of, which is addition of two numbers. So here, what do we need to do to define this operation? So focusing on the verification to start with, we need that all our inputs, so both inputs and the output are, I think it's called signless integer like something like that, but you can think of it as they need to be numbers to start with. But it's not just enough to put some sort of constraint on each of these things, because they need to all, the constraints are all linked together, and they sort of need to communicate with each other. And to see that, so we cannot define each of these independently, because if you look at sort of this generic format below, this sort of satisfies each individual thing in that both inputs are integers and the output is an integer. But this is clearly wrong because we actually need all of these things to be the same type. Here we also get to see this inference problem because the custom format above only specifies this one type, which is actually specified to be the result type. And the operation definition needs to know that it should set the input types to the same as the result type. So how are we going to encode all this? So, this is bad. So this is how we're encoding this. This is sort of a slightly pseudocodey Python way of how we're encoding this in XDSL. But the key thing is that we have this var constraint. And what this var constraint means is that wherever this constraint is encountered, so whenever it's encountered, it should be the same thing. So here we have this left-hand side and right-hand side operands. They're said that they need to be this var constraint, and the result also needs to be the same var constraint. And then we can specify this assembly format. As you can see, the only type given is the result type, as I said earlier. And so the type of the left-hand side and right-hand side hasn't been given, but the system can figure out from this var constraint that actually they need to be the same as the result type. So this is kind of a simple example. So where do we want to go on from this? So basically all these sort of variable constraints can be nested within other constraints that this system has. I don't really have enough time to sort of explore the full range of different verification things we can talk about. But here's one example. So if we have this vector.insert operation, this allows you to either insert an element into a vector or insert sort of a vector itself into a multi-ranked vector. Here so the interesting line here is this _v. and we're saying we've got this vector type, but we're constraining the elements of the vector type to be this other constraint. And this allows us to talk about all these things. The only last thing I'll talk about is that where we want to go on from this is talking about shapes, because this has not done any of the shape verification yet. Sorry for running over.